Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Jack Lissauer, who's come across to us from NASA Ames. Jack did a BS in mathematics at MIT and got his PhD at UC Berkeley in applied mathematics. His subject was the dynamics of Saturn's rings. He then has been a professor at Stony Brook before he came across to NASA Ames. Where he's now currently very active in Kepler, in the Kepler mission, and he recently had a Nature paper published on Kepler 11, which discovered 6 closely spaced planets, and is famous for the analogy to a record that he used in that context. He also discovered with Mark Showalter two inner satellites of Uranus, Cupid and Mab, and he is the co-author of a planetary sciences text with Inky DePater at UC Berkeley. So today he's going to talk to us about a very interesting subject for us all astrobiologically, and that's what Earth would look like without a moon. So if you'll join me in welcoming Jack.
Well, thank you, Adrian, for that kind introduction. It's a pleasure to be here at SETI Institute. I enjoy coming by here for some of these seminars myself, and we indeed had our Kepler science team meeting here one day last month. And thank you all for coming out right after the holidays in the new year to take a look. I'm going to tell you about some research I've done in planetary dynamics, but it's research that, as Adrian mentioned, has an astrobiological application. And indeed, it has an astrobiological motivation. Now, we on Earth enjoy what we consider a benign climate. That isn't always the case and maybe changing somewhat with the increase in carbon dioxide in our atmosphere. But if we look back over the past few million years, we've had these occasional ice ages. They're not strictly periodic, but they are very strongly correlated with small changes in various dynamical parameters of Earth. In particular, changes in the eccentricity of Earth's orbit and in the parameter that I'm going to be focusing in on today, which is the obliquity. The obliquity being also known as the axial tilt, the basically difference, the angle between the equatorial plane on Earth and our orbital plane around the sun. Right now, that's a bit over 23 degrees. It varies over time between around 22 and 24 and a half or so degrees. And that is enough to induce ice ages and interglacials like the one we're in now. Now that happens to be because we're in a very sensitive period in the climatic effects of Earth where we're right at the borderline, but still it illustrates that very small changes in Earth's obliquity can have profound effects on climate and therefore planetary habitability. this is all for the real Earth. We have a moon. The moon is very important in obliquity. So we have these variations that we have. Now, if Earth were purely spherical, then the forces by the sun and the other celestial bodies would act like on the Earth as they would on a point mass and would not exert a torque on the Earth about its rotation axis. But the Earth, because of its rotation, bulges out a little at the center. That means it's not perfectly spherical, and therefore Newton's proof that gravity of a spherical body is like that of a point mass does not exactly apply to Earth. And it's both the gravitational force exerted by the Earth is not exactly the same as a spherical body of the same mass, and the gravitational force exerted upon the Earth, because from Newton's third law, for every reaction, there's an equal and opposite reaction. Now, the main torque on the Earth's equatorial bulge, well, there's torque from the moon and from the sun. The moon's very close. The sun's very massive. The sun's torque actually pulls the Earth around, and this is responsible for the 26,000-year precession of the equinoxes, why we have a different pole star than was used by navigators in the Roman Empire. But that just changes the direction of the angle between our pole and our rotational pole and our orbital pole. It doesn't change the amount. And so it doesn't have a substantial effect on climate. But perturbations from the planets can change the amount. Planets are small. These perturbations are small. They act over much longer timescales. Moreover, since Earth is orbited by a fairly massive satellite, our moon, and a lot of the angular momentum in the Earth-Moon system is in the orbit of the moon rather than the rotation of the Earth, the moon acts to stabilize our obliquity. If the moon weren't there, the torques, these small torques from the planets on the equatorial bulge of the Earth could, over time, build up and cause large variations in the rotation of the Earth. And back in the 90s, Jacques Lissauer did some analyses with various collaborators in France and showed that it was possible for the Earth, without the moon, to have a huge range in obliquities from 0 degrees, so basically no light making it at the poles, or the sun always on the horizon at the poles, very little light, to 90, almost 90 degrees, 85 degrees, so that means the summer pole would be almost directly face on to the sun. The sun would be near the zenith in summer, in the summer pole. And they'd have a very long, cold winter in the other hemisphere. But Lissauer didn't show whether the Earth would really vary over this over this huge range, especially on any reasonable time scale. And by reasonable time scale, I don't mean time scale within our lifetimes, or even civilization, or even humanity, even since the Cambrian. Since advanced life came on Earth, would the variations be anything like this? Because people have seen that these variations are possible. They assume that it would be very wildly varying, and therefore they have huge climatic shifts, which would be perilous to advanced life forms. And therefore people have been saying you need a moon in order to stabilize obliquity, in order to have advanced life. And therefore, since the models of the formation of the moon suggest that only roughly 10% or fewer of otherwise Earth-like planets would have a large moon, a substantial enough moon that could affect the obliquity variations in a profound way like our moon does, then there'd be a factor in the habitability effectively put into Frank Drake's equation of about 10 to the minus 1, or even as small as 10 to the minus 2, that you'd have to multiply. So we'd have only a few percent, 1 to 10%, as many habitable planets as would otherwise be the case if an Earth-like planet didn't require a moon. And so we are looking into are large moons necessary to stabilize planetary obliquities? And what I am reporting to you today are results that are being published in this month's Icarus magazine, which is the results of the first stage of this research project. In particular, we are looking at what the variations of obliquity would be in the Earth if we didn't have a moon. Now, I was saying obliquity affects climate. And this is really the way that comes through. If you had a nice straight up obliquity, zero obliquity, the plane of the equator is the same as the plane of the orbit, you might think that would be a nice calm climate. You wouldn't have any seasonal variations, but indeed you'd actually have very extreme differences between the equators and the poles. Because the sun would never be more than on the horizon. At the poles, there'd be essentially negligible amount of insolation at the poles. Our obliquity is a little bit less than 30 degrees, so we have significantly more heat at the equator than at the poles. If you had something at the other extreme, talked about 85 degrees earlier, the complete extreme 90, the poles, since they would have the sun directly overhead in summer, would actually, on an annual average, have a little over 50% more insolation than the equator. At 60 degrees, it would be slightly more at the poles. It's around 54 degrees when the poles would be equal to the equator. But that doesn't mean the climates would be the same, because the equator would get sun year-round, and the poles would still have a very hot season and a very cold season. But low obliquity is actually at least as big an effect as high obliquity in the sense of annual averaged and getting a snowball Earth and things like that. So this is some work mentioned earlier, almost 2 decades ago. And I won't go into the details. That would take an extra hour or more, and that would assume that you had a substantial background in planetary dynamics. But the results are easy. That the Earth, at its current rotation rate, without the moon, could vary over a huge range in obliquity. And if you tried to predict going forward in time, you'd have these uncertainties which would grow exponentially in time. And here are some simulations that he did on the Earth's obliquity up here and the insolation down here, integrating into the past with the moon, showing very small variations, and into the future without the moon, showing much larger variations. And small variations in obliquity means small variations in insolation, large variations in obliquity by large variations in insolation. Now, that's fine, and you do have larger variations without a moon than with a moon. But you notice here, this goes down to about 16 degrees. It goes up to about 32 degrees, 33 degrees. Much wider range than we actually have. But it's nothing compared to the 0 to 85 degrees that he said was possible. And this is a time of 1 million years. Well, 1 million years, you have variations, but maybe these are variations that life can stand a lot more easily than 0 to 85 degrees anyway. And so we wanted to investigate what happens on timescales that are relevant to life. And really, these variations are important mostly for advanced life, which is from the Cambrian to now. So 500 million years, maybe 1 billion years going back a little farther. We had snowball Earth back then. That was a big change 600 million years ago. And we made it through that. So those are the characteristic timescales. Not 1 million years, but we don't have to do 4 billion either. Now, Mars has tiny moons. They don't really affect things much. Here are some integrations showing that there are fairly wide variations on timescales of tens of millions of years. They're not quite as big as allowed, but they go up to 60 degrees in one case, in another close to 50 degrees. The moons don't have much of an effect. This is a 500,000 year integration because they're so small in the case of Martian moons. This is our result for 500,000 years, very similar to the previous result, just showing that our code's doing basically the same thing. Now, we've run our code on Earth, and we've run it on, this is for million-year timescales back 2 million years into the past, forward 2 million years into the future, and we see, not surprisingly, going down to around 15 degrees, going up to around, maybe 35, 36. This is a little bit longer than Lissauer's integrations. Doesn't get quite to 35, 36 in the future few 100,000 years, which is what he studied. So it's consistent. Now, if you look, we also ran them actually 2 billion years forward and 2 billion years back. So this is back 4 million years centered on the present. This is 40 million years centered on the present. And you know, there aren't much larger variations on 40 million year timescales than on 4 million year timescales. You go down a little bit lower, it gets down to maybe, 12 degrees and maybe up to, well, still less than 40, maybe 37 or so. On plus or minus 200 million years. Now we're getting real interesting for astrobiology. Not much larger. It doesn't really seem to make it as high as 40 or as low as 10, so same type range. If we go back 2 billion years, we see a little bit lower for a short period of time, not much higher. Go forward for the first billion, maybe gets a little higher, but at 2 billion, then it goes way up. So is that the answer? Well, no, it's not the answer. As I mentioned earlier, Earth's obliquity is chaotic. That means it's extremely sensitive to initial conditions. And if you change things by just a little bit, you have a meteorite this big hitting Earth. It won't change things much for millions of years. In tens of millions of years, it'll start changing things. And in hundreds of millions of years, it could make completely different. Now, we don't know what moonless Earth is a hypothetical thing. There isn't a real problem that we could study, even if we wanted to. If we were actually studying the Earth, we wouldn't know whether it gets hit by a meteorite, but we wouldn't also know the initial conditions well enough. We don't know the position of every asteroid, which would have a tiny effect, etc. How do we deal with this? We have, to get these integrations done, we have computers running. What we do is we change the initial conditions slightly, and we run it again. And we run it again, and we've designed our code to do this in a very efficient manner. And we've done a lot of different possibilities. This is another simulation, future obliquity, and it does go down. It was very nice for 500 million years. Then it gets to the state where the poles get hardly any insolation at times. And then 2 billion, another 1.5 billion years forward, and it gets very active. And million and billion are big differences here. For life to develop, at least the time scale it took on Earth, life that's sensitive to these type of climatic variations, we're talking about time scales of hundreds of millions of years. So things varied on million-year time scales, even tens of millions of years. At that level, it could cause big problems for life. But if it varies on time scales of billions of years, we don't really have to worry too much about it. So our study looked at integrations, many problems, slightly different initial conditions, or very different initial conditions, to look at the possibilities out there on timescales characteristically of 1 billion years. This integration, this is 2 billion years back, and it's fairly moderate changes in contrast to the 2 billion year forward integrations. This is the change. If you move Earth 15 centimeters ahead on its orbit, same orbital period, same semi-major axis, but little effects of the planets change things gradually over time. This is the change in obliquity in degrees. Well, up to, this is 30 million years into the future, 1/10,000th of a degree, not much. 100 million years into this future, 100th of a degree, not much. 140 million years into the future, 10 degrees. Yeah, that's significant. So that's why we have to do a lot of these integrations. This is a set of actually 3 different integrations, 2 billion years in the future, 2 billion years in the past for each of them. And one starts with a fairly low obliquity. One starts with a somewhat higher obliquity than we have now. This one starts, and this starts with a very high obliquity. But you see that they vary, but they don't vary from low to really high. There are 3 different ones. These 2 do overlap here. Retrograde. This is the Earth spinning in the opposite direction it orbits. So the sun rises in the west and sets in the east. Think of it that way. Variations are very small. This one, they're comparable to the actual moon, Earth with a moon. And the reason for this was actually known previously, but we've explored it in much more detail, and that is that the variations in obliquity are caused by near resonances between the forcing of the planets and the natural frequency of the oscillations of Earth's obliquity. Now, this resonance phenomenon, mathematically, is something that would be fairly complicated to explain, but it's something just about all of you learned before you were 5 years old, and that is if you are pushed at the right cadence, little pushes on the swing, either by your parent or by moving your legs backwards and forwards, little changes, if they were done at the right times, would increase in amplitude, and you could get large oscillations from small forcing. But you can't do that backwards because they're not in phase. The natural frequencies are not the same. So I'm going to show you now results of a large number of integrations. Up to now, I've shown you how the variations go in time. But the key thing here is what the total range is. Just a few degrees in these cases, a little more here, but still, the range is under 10 degrees. These are ranges, maximum to minimum, of a set of, well, it must be 19 different integrations, 5 degrees off in initial obliquity, which are the dots, and they are 1 million years forward in time, 500 million years backward in time. And the red shows the variations on that 2 million year time frame from 1 million years ago to 1 million years in the future. And the blue shows the whole range going back 500 million years into the past. So you start with 0 obliquity, and it goes up as high as about 24 degrees in this 2 million year time frame. But if you even go 500 million years back, it still stays below 30 degrees. And 5 degrees, you get a little higher. 10 degrees, well, it's not much higher. 15 degrees, little higher again. But you see characteristic ranges of about 20 degrees. Some of them are a little higher, some of them are a little lower. 20 degrees is large compared to the actual variations of 2.6 degrees that we have with the moon. but it's very small compared to that 85-degree range that's allowed and that probably would be occurring if we did these integrations not for 500 million years, but for 500 billion years. But the universe hasn't been around for nearly 500 billion years. So for the fundamental astrobiological applications, these are the right ones to look at. This is for rotation at the period we have in the prograde direction. Retrograde, opposite direction. Very small variations no matter what the obliquity is. And we have an obliquity around here, somewhere in between these two, would be like ours except in the opposite direction. If we were rotating retrograde at the same rate we are now with the same axial tilt, things would be very similar. There'd actually be one more fundamental difference than if than the sun rising on the other side. We'd have 367 days a year instead of 365. Because we actually rotate 366 times a year, 366.24 if you want to be a little more precise. But once is to make up for the fact that we're going around the sun in that direction. So these are just putting them together, showing the large variations for prograde, the small variations for retrograde. There are different models of the origin of planetary rotation. Some say half the planets are retrograde. It's a really hard problem.
Planets in our solar system?
Half the planets everywhere, theoretically, Earth-like planets. Not real close to their star, so the tides would have done something to them substantially. Not big gas balls. Those aren't relevant for astrobiology. And so this problem has been worked on for a long time, since Pierre-Simon de Laplace in the 18th century. So we don't know if these are as common as these. Maybe we will in upcoming years or decades. Decades, I would think. Years, not so sure. What if we were rotating faster? Half as long a day. And actually, Earth was rotating when it was soon after the giant impact that Mathieu mentioned in his talk of the origin of the moon and tidal evolution of the moon. Earth was rotating a lot faster. Retrograde, again, very stable. Prograde, it turns out, for low inclinations, low obliquities, you'd stay within very confined range. For somewhat higher obliquities, you'd have very wild oscillations. 16-hour, similar to 12-hour, actually. 16-hour day. 20-hour, something different. Low obliquity is very high. In all cases, retrogrades are much more stable. But the progrades vary with the specific initial obliquity and with the 20-hour period. And these are very wild ranges, much larger than we would have with our 24-hour period. 30 hours, now it's getting to be smaller variations. And it's just having to do with the particular frequencies and the amount of torque you need to change the obliquity and the positions of the planets within our solar system. And indeed, what we are going to be doing is integrations of theoretical and observed extrasolar planets. Because the Earth, the moonless Earth, is really just a stand-in for these other systems, and the first thing we wanted to look at. 36-hour period. This is just the insolation versus latitude plot again, showing that it slightly different values. 23 degrees, the poles get about 40% the insolation of the equator. 45, fairly equally distributed, but again, even though the poles look about the same as the equator, they have seasonal variations that are much larger than in the actual Earth, whereas the equator has much milder seasonal variations. So this is pretty much a summary of our results that I showed in the many previous slides. The variations as function of period and of initial obliquity in all cases from 12-hour periods to 36-hour period, retrograde obliquities, all of them are very stable. The variations that you get, and this is on all half a billion year timescales, for some prograde obliquities, for some periods, are fairly moderate. For other combinations of period and initial obliquity, you can have very wild swings, not quite from 0 to 85 degrees, but pretty large, a good fraction of it in some cases. So, bottom line is that, yes, the obliquity variations of Earth would be larger if the moon suddenly ceased to exist, would be substantially larger. But they would not be anywhere near as large as one would have predicted from the analysis of the allowed ranges. So this is indeed a factor, variations in obliquity of the typical terrestrial planets, 90-something% of which lack large, long-lived moons, if our theories are right. But it's not as severe a factor as various people, including the authors of the book Rare Earth, that many of you may have read, pushed. And so for those of you who are looking for life out there, or interested in following that search and want it to be found, it's not as big a problem as has been thought by most of the community over the past 2 decades. And we're going to be doing some more research in the upcoming years to see where in that range of difficulty specifically things are likely to lie. Stay tuned. Thank you.
Jack, this is fascinating stuff. I see there's lots of hands up. I'm going to take my prerogative of asking the first question. So it looks like we're the freak planet. If it looks like retrogrades are where you want to be if you're looking for life. What potential ways are there to find retrograde planets? And does Kepler have any chance of looking for the rotation of atmospheres or something like that or perhaps JWST might be able to look for rotations of these planets?
Good question. It's not an easy observation. You have, first of all, you don't care about the hot Jupiters. They're not relevant here. They're tidally locked. They're not subject to these things. you can get, in principle, rotation rates from a transiting planet if you have really good signal-to-noise observation of the transit, and you see how the planet cuts across the limb of the star, and if you have really good signal-to-noise, so bright star, big telescope, you might be able to tell the shape of the planet being flattened because of its rotation. And even maybe its tilt to the direction it's moving. But whether it's moving forward or backward, that's going to be really tough. I would say the two best hopes for a terrestrial planet within the next 10, 15 years would be TESS, which is kind of a mini Kepler but focused on planets closer, because it's an all-sky survey. If TESS gets lucky and finds the right planet and observing technologies go forward, or if Jill finds somebody out there who can tell us.
From what you said, it looks like Jupiter is one of the important planets around. Have you played with the size and position of Jupiter in relation to Indiomath?
We have not, but this is part of our future study, because that's the extrasolar planet. This was a fair amount of computer time, and we wanted to test these planets in our first investigation.
Yeah, but what is the amplitude that you expect by moving Jupiter, size-wise and position-wise?
Well, you can say that smaller Jupiter means smaller effect, but that's actually more true on short time scales. We don't know about long time scales. The problem is we have resonances. And if you move it a little bit, you could bring it closer to or farther from a resonance. So you don't want to just do one or two. You want to do dozens of these cases. And this is a very relevant region of parameter space, but we haven't done it yet.
Okay, to follow up on hot Jupiters instead of our cold Jupiter, there's I guess you haven't investigated possible tilt of hot Jupiter planes.
No, that's a very different
Yeah.
problem
Yeah.
because you have tidal forces that are very important. They need to be taken into account on any substantial times, and things are likely to damp. The theories of tides aren't that well formulated for some of these objects, and they're just not of astrobiological importance as far as we know.
You didn't take, or at least you didn't talk about the effects that the moon is moving away from us slowly, and what effects on your calculations would that cause?
Not at all. We don't have a moon in our calculus. We're doing things assuming there were no moon.
Okay. Had no moon at all.
Yeah.
This may be beyond the scope of your talk, but the tidal effect of the moon regenerates atmospheres and lets gases circulate due to plate tectonics and all that. Have you given any thought to whether or not that would be relevant as far as not having a moon to do that, make it more hospitable or inhospitable?
I think, as far as I know, it's negligible on those effects. The thing that it would have an important astrobiological effect is the tides, in the sense of the shallow seas where organics could be concentrated for the beginning of life. But that's just a matter of a factor of a few, in the moon being bigger effect there than the sun. So
I have a similar question. Does the mass distribution of the Earth change your calculations, like glaciers growing and receding, or Pangea breaking up into 8 continents? Does that affect your calculations?
If we were trying to do calculations for the actual Earth, it would. It would be a lot, those things would be more important than that little meteorite, hypothetical meteorite. But we're not. We're just trying to survey a possible range of hypothetical other Earths, so it doesn't matter.
But for the actual Earth, conceivably, in the time period you're talking about, we could get a bigger range than you calculate.
Depends what you mean by actual Earth, because we have the moonless Earth, which isn't the actual Earth anyway. So, but yes, it's possible that these small changes could be relevant.
But what you assume the asymmetry, the only asymmetry you had in the Earth was the bulge.
The equatorial bulge, yes.
But it was a constant density Earth with
Right.
the bulge.
Right.
So, I mean, the moon still stabilizes the Earth's obliquity. I mean, so that is a factor in climate stability in the Earth, isn't it?
Yep.
So, I mean, that's to defend the rare Earth hypothesis, at least with regards to intelligent life, and this is SETI. It's, I mean, obviously, without a moon, the Earth would keep its life, its, you know, even its simpler multicellular life, but to actually get to be stable enough for intelligence to arise, you might make a case that you still need a large moon to keep things from, you know, having long ice ages and things like that that might actually kill off intelligent life.
Well, if you allow retrograde obliquities, then the typical variation of a moonless Earth in its obliquity is comparable to the variation of the actual Earth with the moon. If you say that obliquities are all going to be prograde, then it's intermediate between the ranges calculated a couple decades ago in the 90s, the very large ranges, and the very small ranges that we actually have with the moon.
So somewhere in the galaxy, there's a version of you on a retrograde planet arguing that only retrograde planets can support intelligent life.
There are views of this that if you have an open universe with an infinite amount of mass, then yes, but not in our galaxy. Our galaxy is way, way, way too small for there to be room for another one of me.
Gee, that's a shame, Jack. But I actually like to, counter this love of the retrograde, low deviation, we actually don't know that we might have evolved to higher complexity and intelligence faster with greater environmental stresses. So we tend to forget that. We tend to think that if you want to be here and just like us, you need things that are nice and stable for a long, long period. But it might have been that other places, evolution would have gone faster. And all I can say is this is a really timely publication now that John Gribben has given us Alone in the Universe just before Christmas to revisit the whole rare Earth, mainly on the basis of the moon.
So, Snowball Earth, obliquity changing may have been a cause in initiating that. And what are the estimates of Earth's obliquity during that time period?
I don't know of any good estimates back then. You would have a slightly different dynamical situation with the moon being closer to Earth, and that could be calculated. Mattia, do you have any comments on this?
They say that it's the distribution of continents on the Earth that led Earth to a different regime.
Yeah.
Now we oscillate between short ice ages and interest ice ages, but Back then, just the continents were all at the equator, they say. That's what I heard. And
Okay.
you could cover the seas with ice, and then you could have a global ice age, which you can't have now.
So what Mathieu is saying is that he thinks that the variations in the position of the continents, even back at 500 million years when the moon was non-trivially closer, was more of an important effect. And it certainly has been for the past tens of millions of years why we are in this glacial, interglacial age and have not been for hundreds of millions of years. I'm just not, I'll defer to Mathieu on whether the moon changes the natural frequency of variations on those type timescales.
Is there anything in planetary formation theory that gives us an idea of what percentage of planets might actually have a retrograde spin?
There are a variety of models. I worked on this extensively, and I wrote several papers on it in the 90s, and included in those papers in early aughts. And in those papers I had long appendices of the history of the problem, the study back to Laplace. And the answer is we have some good ideas on what's going on with the gas giants, and that they are likely to mostly be prograde. For the terrestrial planets, the standard models, most of the standard models, suggest that the quasi-random effects of giant impacts are likely to be dominant, so that for such planets that are not real close to their star, which have major tidal effects, there would be a comparable number of prograde and retrograde. Not necessarily 50%. If you did 1 million of them, there'd probably be between at least 300,000 prograde and at least 300,000 retrograde. And exactly what would be in the middle, and then there's the other issue of whether you'd get a little bit of preference to low obliquities versus, which is 0 or 180 versus around 90. But it seems like there would be a fairly large range of possible, and it's not that there are any that are real rare.
So if you can't blame the obliquity variations on Mars on it not having a nice big moon, what models do you like?
Well, Mars is a prograde rotator, and different planets have different frequencies. Mars is near the big bully of the solar system, and it varies by something like 60-degree range. The previous model suggested that Earth would vary by an 85-degree range, and what we're saying is it's more like 20 degrees. So,
one last question. How is this modeling that you're doing with the team informing the Kepler team or the Kepler science teams on maybe what to study as they locate these candidate planets?
Well, first of all, this is not part of my Kepler work. And it's really complementary. They both give information about planets, one in a theoretical sense, one in an observational sense, but there's not a lot of feedback between the two at this point.
Okay, that's about it for question time. If you have any more questions, or if you are not courageous enough to stick your hand up, feel free to come up and talk to Jack for a little bit. Jack, we have a special Are We Alone SETI mug here as a commemoration. And please join me in thanking Jack for his great talk.